तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last demonstration of simulator, we saw 8 input mux, and we'll continue with the same. We'll quickly have a glimpse of what we had done in mux and continue with demux and other circuits. First complete all the combination circuits and then go over to sequential circuits. And to start with, we have this is the code that we have written already for 8 input mux, and using an always statement. I am not going into the details. It's just enough to point out that I0 through I7 are all assigned to mux depending upon the ABC conditions of the input. This has been adequately explained a couple of times earlier, so I will not go into the details of that. And pictorially you can see this in the PowerPoint, and this is what it is. And we saw the waveform for this mux, and there are two waveforms as such. The last one gives the actual outputs. So we have seen I0 through I7 and as a pulse applied at varying points of time at every 20 nanoseconds, if I remember right. And finally we had this waveform, which this is the mux site, and corresponding inputs, this is I0, I1, and since ABC keeps on varying in the binary fashion that you have already seen, and you have actually 3, 6 here and 7 here, and the 8th one is here because I have forgotten to deactivate. Of course, that's it's a material rather. And so you have totally 8 inputs corresponding to the I0 through I7. And now we will move on to the demux, and we'll first have a look at the code. This is the demux. This is exact inverse of the mux, and we feed the mux 8, which was the output for 8 input mux, into this demux. And once again you see it is based upon the select pins ABC, and as per the ABC value you have D0 through D7. We have also mentioned that we should not forget to reset all the other outputs, and only that output under question needs to be input from the mux 8. What we are doing is inverse of the mux 8. So what we put in as input for mux 8, namely I0 through I7, and we will get the corresponding D0 through D7 as the output, which will be the very same as the I0 through I7 that we have. And we have also seen a default condition at the end, towards the end, and which resets all the outputs, because in the course of the circuit working you may encounter X in any of the bit position, or even Z, which is indicative of a tri-state condition. and so you take it to a safe state of resetting all the outputs under such extreme condition when such invalid signals are applied. And the same demux in the PowerPoint what you have seen is pictorially depicted here. This is mux 8 output connected. Note that ABC is the same select pin for the demux here, and A is MSB, and mux 8 is input here, and out comes D0 through D7, and D0 is the very same as I0 and so on right up to I7. And the waveform for this one which has been obtained from model sim, and because it was not visible when we did real time, and I have made it into paint shop, and I have that magnification is far better, resolution is better on TV monitor. That's why it has been done. And that way, there are actually two files as such. One is this here. This is the demux. Now ABC are the corresponding inputs which go in the binary fashion as such, 0 0 0 0 0 1 and so on, and till the end. And this mux 8 is what you have already seen just now, corresponding to I0 here. This is mux 8, I0, I1 and so on, right up to I7 which was flat on top here. And so what we expect here is D0 through D7 as the output for the demux as such. So as we said before, I0 was just this waveform, and thereafter it was flat 0. So naturally if it is working correctly, you should get the very same waveform. You should recover back your inputs. And let us see D0 first. So that is precisely what you have here. So you can see this here, D0, then D1 here, and you can see it is flat thereafter at 0. Just single pulse is got. So this way it will be very easy for you to cross check. So you can plow one output into another module and then check it out, and it will be very handy that way. And probably you can adopt such strategies while designing any circuit. And once again we have time base here. It is marked here at 50 because this was actually when copied from the model sim into the paint, it was expanded as such before copying. So that's why you see a different scale from 20 nanosecond earlier which you have seen. And so then we move on to these other outputs as well, that is there in this waveform here, this file. So we had seen D0 and D1 there, and D first at this position and this position. Now third position you have D2 here, and you can see here time base is also same 50. So D2, D3, D4, D5, you can clearly see all of them going all by one clock period as such. In fact, being combination, there's no clock period. It's every 20 nanoseconds that's happening. So the final output you see it remains at 1 as such. So this completes demux as such, and we'll move on to the next one called the magnitude comparator. Before that, we'll close this. We have seen already full ladders, and we'll move on to the magnitude comparator. I hope we have not seen this earlier in simulation. And here you have two numbers N1 and N2, each 8 bits in precision, and if N1 is greater than N2, you activate F13, and so on. For less, you activate 14 equal to this, and so on, right up to this F18. This symbol is greater or equal to the nomenclature that you adopt, less or equal to and not equal to. And we'll see the waveform for this corresponding. And before that, we, if you want, we can have a look at the code also that we have already written. So that is this here. So it is in an always block as such. Is this the one which you are doing? It's not this. I think this one. This is the magnitude comparator. So depending upon N1 or N2, it's the always block we had used. So it's a simple assignment as you see in the depicted in the picture on the slide, and that's what you have for up to F18, which is greater, exactly the same what you have seen on the slide. And coming back to this, going to the waveform for this, we have here 1 minute, just see where it is. It's here. So this is the waveform. So what is listed here is N1. This is combination circuits test bench, and under that these are all the signals N1 and N2. And just now we have seen F13 through F18 as such, and these are all the outputs here. And first, only two numbers are there. You don't have to remember. So the first one. Now you notice a difference here. All along we have been using only single bit here, indicating a binary signals, and now we are dealing with a multi-bit signal, because this N1 and N2 are actually 7 through 0, that's 8 bits here, and therefore you see a bigger number. And we'll also see the model sim how we set these menus as such. And let us see, we are doing a magnitude comparator. So now how should it function? Let us see. 200 N1 is N1 and 199 is N2, and if you compare the two, naturally you have 200 greater than 199. Therefore this signal must be on, F13. That's what we have here in the pictorially depicted. N1 greater than N2, F13 must be on, then less and then equal to. We'll just swap between these two, then we'll get a clear idea. And so you can see here. So if it is 200 greater than 199, it goes high here. This bit alone, this is the output here, and thereafter it remains low, because nowhere else that condition is satisfied. It is less here and it is equal to here. And now we can see if it is less, this must be activated. So you see here this remains at 0. Yes.
Shouldn't F18 also be high?
Yeah, we'll be coming to that. We'll tackle one at a time so that we are clear. And F14 is less, N1 less than N2, and so here it is greater. Therefore, it has got to be 0, and it goes high here only during this transaction condition. So 100 is less than 199. So N1 is less than N2. Therefore, it goes high and remains low all through. Other than that. And similarly, F15 we have seen as being equal to N1, it is a condition for N1 equal to N2. So this doesn't happen here, therefore it remains F15. So that remains 0 here, and it goes high only when it is equal to. You can just see here, 255 equal to 255 and beyond same. So it goes high here, till then it was 0 here. And let us see what the other one is. F16 here, F16, 3 of the outputs we will consider. We will go back to the slide and see what they are. So F16, this is what you are asking, and N1 not equal to N2, and the other one is less or equal to, greater than equal to. Just remember this so that we don't have to come. Not equal to, less or equal to, or greater or equal to. So in this case, this one, right? This is greater, not equal to. So this was equal to condition. So not equal to will be exact reverse. So we don't have to look at even the inputs. So it is high here for F15 being 0, and it goes high thereafter, and here it goes high here, low. So that's what it is here. And so that proves that not equal to is also working. And then here it is less or equal to. So if it is less or equal to, so first one we started with a greater there, so it goes high, low, and this goes high because this is greater or equal to. So we can club together and deal with it here. And here it was N1 less than N2. So this goes high and this goes low. And for equal to, this is the case here. So we are dealing. What are we dealing with? This is less or equal to or greater or equal to. So equal to is not satisfied here. So naturally it is 1 1 in either cases. And we'll move on to, we'll close this window and then see what more we have in next one is, I think this is the last design example in the combination circuits. And you have here, just to recapitulate what we had done earlier, I'll just state quickly what this is. We had two numbers, number 1 and number 2, each being 8 bits here, and these are all the inputs from the user. If enable sum is high, only then this computation will be done. This sum will be done for this, and then output on this. The sum will be 0 if enable sum is 0 as a low or inactive, and the actual sum will appear here only if it is 1. And so is the case for other outputs match more or less, which simply means sum equal to preset value. PV is abbreviated here. And note that when you add two numbers, it will result in one more bit extra. That's why it is 8 through 0 here. And we'll see, this is some example. So let us see once again the actual code for this. And this is what it is here. And we have used a mux here based on enabled sum being high. This is the question mark is for the mux. So you just compute add signs here. And I think I showed this on the board earlier, and I might have left out some bracket. I think I left out bracket. It will have to be in place normally. You can check it up. You can just remove the brackets and run through the compiler and find out whether they are absolutely required. So it is always preferable to have brackets where possible, as we have mentioned before. And if this is satisfied, the sum is allocated to this. Otherwise, 0 is output into the sum, and that's what it means. If enabled sum is 0, 0 will be output. So is the case for more, less, and so on. Only thing is those conditions will have to be satisfied. For match, more, match is same preset value equal to sum, then more and also less we have seen here. And we'll see the waveform for this corresponding thing. We have already seen the slide on this pictorially, and we'll see the waveform for this. This is sum. So we have an enabled sum here, and number 1 and number 2 are there, and we have also a preset value here, and you can see the entire waveform window. You can see with more clarity here in the real-time emulation, simulation as such. We couldn't see all this clearly. I hope you can read this file. Are you able to read this on the monitor? This is file, edit, cursor, zoom. I wonder whether you can. And there are different symbols here, and this is the usual cut. It's very same as any Windows commands as such. And this is a floppy is for save and open and printer and so on and so forth. This is the cursor I have been mentioning earlier. If you click on this cursor, a dotted line cursor will appear here, and you can remove that by clicking on this. And we have also seen how to use transitions of waveforms, whatever you had marked or highlighted, by merely pressing here, and along with shift, if you press here, all this will be highlighted. So whichever signal you want to highlight, you can use that one. In addition to this additional signal you want to highlight, you can use control and press at the decide point. So once again, if you press at already highlighted thing, control and on the signal, that signal will be deselected. So it's very easy. It's same as any window platform. Window platform uses very similar things. And you have a cut we have seen. And so these are all zooms here. You can zoom in here. I think factor of 2 will be there in zooming. And zoom in, that is to expand what you see on the screen. And you can zoom out here. And this is for, I forget that. I think I'll come to that. It's not clear from here. I'll see in the simulator and tell you. One of these is for the entire full screen. So whatever simulation you have done, the entire range is automatically fit in the one whole screen as such. And that is either this or this. We'll see what it is. And I remember not here. We'll come to that. And there are other things which you can, what you have here, you also have some help in the main menu. This is not the main menu. It's only a wave menu as such. So in the main menu you have more, and you have also a help facility available. A documentation is also available, which you can download from the using the internet. And so there are so many other symbols. You can just get familiar clicking one menu after another, and then it will be clear to you. I hope you have these platforms at your premises so that you can experiment on this. And now coming back to this application as such. So when enable is low, no activity take place, and that's why you see here for number 1 equal to number 2 preset, all of them, this is through the test bench, right? And I hope I don't have to show the test bench. If you require, I'll show it. For this condition, number 1, number 2 and preset value all being 0. So what do you expect the output as? Should there be a sum or not? Unfortunately, the correct value is shown here, but actually it doesn't really compute here. The reason is this enabled sum is not active during this. So you can verify this by examining other signals. For example, if you add, you will get 0 here, and when you compare with preset value, it is equal to. So you should have a match output, but here the match output is not there. So this proves that this enabled sum is working. That means enabled sum is not active here for this duration. This timing here is 10 nanosecond. So if you look into the test bench, I would have made appropriately using hash 10 and so on. And going to the next one, let us take these values. And now you see that this is enabled sum, first line here, row, and it becomes it's enabled at this point. And so 250 and 250 are the two numbers. When you add these two, you get 500. This is the sum. So it's happening correctly here. And now let us see what else is required. So what is this and what are these? Let us have a look. Oh, that happens to be the preset value, not the sum. I pointed to the wrong thing. That's a preset value, 500. So what we had is two numbers here. When you add, it amounts to 500. That is this one. This is the computed value, and it now you can compare 500 with the preset value. This is the preset value. So equality is seen here. So match signal must be on. Is this the match signal? Let us see. Yes, this is the match signal. So you see here, it was 0 all along in either directions, and it goes high only during this equality being fulfilled. So next condition is 250 and 251, and this amounts to 501, and we are comparing with 500. So it is less now. So what should go high is this less corresponding thing. Oh, something wrong. Sum is greater. So once again I made same confusion. Sum is not first, it's a preset value, and sum is later, right? So it is greater. So more will be activated. And the last one is the less. Let us see that. We'll examine that once again, just to make sure that it really functions. So 250, so we are here and then here. This is 250 and 251. It's 501. This is sum. Compared with sum is compared with this. So sum less is greater actually. So it activates more signal. More is this one, and then less signal is activated at this point of time. And once again, before that one, I deliberately made enabled sum once again low, just to show that it is still working. At any point of time, you can make this. So when it is made low, it's once again it ignores. You see there is no sum there here, and preset value is input condition, so it continues wherever it was left. So here it is 505. That's absent here. That is the reason being enabled sum is inactive here, and once again it is made active here. And all this, mind you, are stimulus applied through the test bench. Yes.
When the enable sum is deactivated, your sum happens to be 0.
Yes.
What if the actual sum also is 0?
We have already seen in the beginning, no? When sum is two numbers are 0, preset is also 0, sum is also 0.
But that is when enable sum is low, isn't it?
Yes. and here also it's same.
No, what
the
I'm
moment,
telling is when the enable sum is high.
In between you mean, not at the
No, when the enable sum is high, and when both the inputs are 0, my sum will also be 0.
Yes.
How will I distinguish between that and the 0 when the enable sum is low?
Just by looking at the enable sum you will know.
Shouldn't I make it like if the enable sum is low, the output should be in a high impedance state or something?
It is, this is one such example. Okay. Depending upon your actual circuit requirement, you will be designing. You can do that way also, right? So you had used a mux there. So instead of putting 0 there, you can say z there. So a tri-state will appear there. Or you want x there, you can get that. Or any other data that you want to output at that point of time, when that thing is satisfied, you can always put there, right? The second input that we have seen here. So we see here. So because it was made 0 here in this, so 0 is appearing. If enable sum is low, promptly comes this 0 over to less, and so is the case for sum. So if you want a tri-state, remove this one, just put z there, right? One stroke b z there. So tri-state will appear there in case that's your need. If x, you can put x and so on. Any other data, there's no, of course, it should match. Being 1-bit number, you have to give 1 bit, not higher bits. So otherwise, compiler will complain. And now I think we have completed this combination circuits as such. Probably less we did not see. The last one. So less goes high, and no other signals are activated. So only among the match, more match, less, only one is activated at a time, because only one can be satisfied. So you can see the last value is 100 and 255. When you add, you get 355. That's sum, and this is less than the preset value here. Therefore, less goes high, right at that point of time, say at 49. So you can have a look at the test bench there. See, in fact, it's like a labyrinth. We'll have to trace completely. I think I'll leave that as an exercise to you. Right? You had to, if you go through that, you'll see that precisely it's the same. Right? I have gone through that. I'm convinced. You can also convince when you key in yourself. Okay, this completes the combinational circuits as such, and we'll go on to the sequential circuits. And before this, we'll have a look at the model sim once again. Yes.
You also said the output can be viewed as a binary string. Suppose I have 16 outputs.
Yes.
I can't see, instead of seeing 16 waveforms, I can club it together and make it as a binary
and we are going to see it now.
Okay.
Right? So when we touch the shift register, that will be, you will be seeing that precisely. Let us open the project. Let us say we want, it's in combination circuit. If you want, you can operate right from this project, or you can open a new project called sequential circuits. And let us say, do you have sequential circuit? Okay, let's not worry about that. We'll just see where we are. So we'll operate right in this. There's no harm in operating in that. So we should click on this library, and probably next time I'll show a blotted up figure of this so that you can view each and everything. Right now it will be very difficult for you to know, and you may see very little activity going on. And it's because the font size is much smaller, this being set in 1024 by 768 resolution, and you have file resolution much less, and also because of what you call, you can't distinguish fine lines on the TV, and that's the reason why you are unable to see this live as such. and we'll have a look at the sequential circuits here. Now what we'll do need to do is we have to compile the sequential. It is listed here in this. So here, as I mentioned, the circuit design is sequential circuits, and it is there included in this file. So when we double click on this, it will do the compilation of both the right here. So once it is compilation is done and no errors are encountered, you can safely go to the load design. So in this you have you invoke this, double click on this, and it has come as work sequential circuits underscore test, and you load this here. And while loading also you should not get any errors. There may be some warnings, right? Here it has done the job. So now next step is to use view, then signals, and you have the signal window open with you can see some of the inputs here partially. You can see, you can, as you take it here, you can see all the IOs listed here, and you can get it as a waveform. Go to view, then on this signals in design, right? And here it opens the waveform window here, and let us run this. So for run, this is the command here. Run all is there. So in fact, I showed in that waveform also similar such thing was there. So here we saw that it's only zoom area here. The third one I was saying earlier, I pointed to zoom in, then zoom out. Then third one is the area you can zoom if you want, and you can zoom the complete your entire simulation. You can zoom to that extent. So we'll see all that once again. So let us run this code. Now you see different waveforms. I wonder you may not be able to see on the monitor, TV monitor anyway. And it also had stopped at a particular point of your test bench, and this is source file automatically opened here. And this also will be very difficult for you to see. I'll just close this, and I'll just indicate. You just take note of only the words that I mentioned, and we'll go on to the waveform as usual using the paint later on. And perhaps you may be able to see in a faint manner here, and it's very extremely faint. Only the clock is seen here, and other things are almost practically unreadable. And you have here all the IOs listed here, and there is one vertical bar here. You can just hold on to that and drag here, so that you can see the entire thing without any obstruction as such. Similarly, you can take this also and then move it here, so that you can see this is what you are asking, 0101 etc. it shows. So this will be looking at exporting to the paint and seeing that, and we'll see function by function. Otherwise, you will get drowned in this maze of signals here, and these signals I can drag to any amount. So these are all sequential circuits. So this will be extremely painful for you to read unless you have this simulator on your computer and working up and working. And now let us go on to a particular thing. We started with sequential circuits. Here, this is what we have already seen. We just had a simple D flip-flop Q and Q underscore N being set to 0 to start with, and then the normal course of normal working when reset is not applied, and we take D input or its inverse and assign to Q and Q underscore N respectively. It's a simple D flip-flop, and we'll see the waveform for that. No, it's here. So here we have reset N, clock, D input and Q. So it's quite simple for you to find out. So whenever you reset the Q and Q bar, right? The moment you reset here, Q is made cleared. It was 1 here, so it is cleared now, and Q underscore N is made high. So Q bar basically. And now subsequent to the reset being on after small duration, this is the reset, power on reset we can consider here, and after that it has got to be high in the normal working state. Only beyond this the circuit will start working, and now what we had to look for is the clock transition. We have written a positive clock transition as such. So whatever is the D input, Q input will get the value. Now let us see here, it was already cleared. So right at this point, reset is applied right up to this point, and beyond that the very first positive edge clock is this one. So here at this point of time D is 0. So this 0 goes through and gets registered in Q, and unfortunately this happens to be the very same state initialized condition. So you don't see the difference here, but you will see when D is 1. See, for example here, it happens, it's being a synchronous circuit, it will always happen only at the clock transition time. So the next transition happens here, and only then the Q goes high and its inverse goes low here. And this is quite simple, and once again a time base depicted here, and we have covered all the possibilities. D flip-flop is the most simplest of flip-flops. So we will close this and go on to the next here. So the second one is, we had a register, a delayed register, and as I mentioned, this is for one of my projects I have handled. It's called video scaling. In this video scaling is to take a motion picture or even a still picture of low resolution, let us say 800 by 600 pixels, and transform it on real time right at 30 frames per second into a high resolution picture, say 1024 by 768. And for that, when a pixel will be out at every clock pulse, and the clock rate may be say 50 megahertz or so. So that means you can process 1024 by 768 pixels, color pictures, motion pictures at 30 frames per second. And for that, you have also to have another signal indicating when that pixel is valid. And for that, I had to generate this one. How it is generated? In fact, this generation is already done here at this specific edge of the clock. That is one clock prior, beforehand it completes. So I just want to delay that computed value by one clock pulse, and therefore I put one more register. That's what I had explained earlier. And these are all reset condition, and if you want, you can set this register and or once again reset based upon some other condition. So this is power on reset, and this is reset for satisfying some other condition when you don't want really the when the pixel is not valid, you may have to reset. So we had to do the setting and resetting accordingly and judiciously. And there's a clock input and also a hold, just like any microprocessor based signal system as such. And the set point will happen based upon the A bar, B, C bar condition being satisfied, and A, B, C condition satisfied, it will set the reset the this is the one reset. So this register will be reset here, and whatever is the register value here will be delayed by one clock pulse by registering in next register, and out comes the desired value that you need. And going to this let's not go into the model sim because it's too crowded, we can't view, and for your sake it has been zoomed out and then stored in Paint. We'll see that once again, and that is here. This is, so you have a reset clock, then hold. Probably hold is not used, so I may let's not worry about that. Clock is a train of pulses here, and reset is active here. Only at that point of time, the two registers are pixel out P, that's the first register we saw, and pixel out valid, and this is the actual decide one. So that's something is happening here. We'll see what is happening, and we have also seen this will be set at a particular point of time for some condition of ABC, and reset at another point of time. And before that, let us see at a reset point what happens when it goes low. What you need to do is reset all the outputs as such. So that's what is happening here in this condition. And mind you, these two are assigned statements basically, so they are all combinatorial outputs. So that will not be reset naturally. And coming to the normal operation, that is right from here and subsequent positive edge, it becomes active only at that point of time. So now let us see, only thing you have to remember is the last three here are the ABC inputs. Once again it is in binary progression, and now let us see what happens to this set and reset. Let us see this. Set is here, we have seen, I think it is A bar, B, C bar or something. So let us see this here. This is A bar, then this is, okay, it happens here, set pixel out, right, setting the pixel out, okay. So it happens here for A is 0, this is B is 1, so it is A bar, B, C bar. Set output goes high here only for this duration. Similarly, reset will go for this, next one is reset thing here. It goes high only for this condition. This condition is what is ABC? The last three on the top will be ABC. So here it is 1, 1, 1. So that's what we had here in this. See here A bar, B, C bar for set and ABC for reset. That's what we had here. And what remains to be done in this is pixel out p valid and pixel out valid, right? And notice that I said pixel out valid is precisely same output as this, and only difference is this will happen 1 clock pulse later on, because that's what the time I want to pick it up, and output saying that pixel is valid right at this point of time. And user can process further when this is asserted, and he can take the actual pixel value, and if he has a storage elsewhere, he can store at the positive edge of the clock subsequent to the rise of this. So it therefore indicates the validity of the pixel. And coming to this here, the last two are pixel out, and so you see here pixel out P is here, and this is staggered by 1 clock pulse, and when it goes low, this also follows suit. So it is nothing more than this is the basic logic in pipelining registers also, which we will see in more depth when we go to adders and other multipliers, arithmetic expressions, how to evaluate them, compute them, how to evolve new algorithms for that also will be seen in that. So you have seen pixel out p valid and this being staggered just by 1 clock pulse. And if we explain this pixel out valid, why it is happening here and why it is going low here, that would complete this two registers used as in a pipeline, or it's just to create a delay as such. So now let us see why it is going high. It is going high here, right? Let us find out why. And how, so we have already seen. We want to, if you look into the code as such, so this is A bar, B, C bar, we have seen set pixel out. This is an assigned statement, therefore it's a combinational, and ABC is for reset, we have seen, and at positive edge of the clock only we are taking action here. And pixel out valid is reset here, and hold we have not simulated, use the hold. Perhaps you can take it up and find out whether it really holds the signal at that point of time by activating it. And so otherwise, you if set is set, 1, then pixel out p valid is made 1 now. So this is the condition that it has gone high. So when A bar, B, C bar goes high, with the subsequent positive edge clock, you remember that we are writing the always block for positive edge. This also must be satisfied. Only then you will go into the reset set mode as such here, this thing. So let us verify that particular thing here. So here what happens is, so you see that set pixel point we have just now described, and it goes high. So immediately here, and it has to go right here, right? It doesn't go. It's delayed because it has to wait for the positive edge of the clock to come thereafter. So that's what is happening here. You just remember it is somewhere here, and the positive edge of clock must appear here. Let us see, go up and find out whether the positive edge happens on that line as such, right? So this is the line, right? Although we that is combinational logic as such. So now this is in synchronous mode. So any register will always be a synchronous type, and it will happen only during the positive clock edge transition. And that's how you have set the pixel out P here. And we have also a reset here, and that condition is satisfied, and it remains high here, and this after a delay you are getting here for the final output, and it's going low here because this has gone high. This is the reset pixel out, right? So this is the reset pixel out. So because it has gone high, and what is happening here? But it is going low because it has to synchronous. It has to be synchronous with the positive edge of the clock, right? This has happened right here, but it won't take action here. Only at the positive edge of the clock I can take. On the other hand, had you decided negative edge transition, you could have written instead of pos edge in that always block a negative edge, right? But for the same signal, you should not put positive edge clock or negative edge clock. It is a violation, right? Tool will reject that. And so we'll close this window. This is also not required. And what we have here is a counter here, right? So we have seen the counter. The counter is quite simple. You have a reset count, then advance count, then overall reset is there. So when counter equal to 255, then this reset count is applied, and this is power on reset. You advance, that is increment the counter only if this condition is satisfied, which is ABC, right? It's quite simple, and out comes counter register, and a counter next was also used inside. That will you'll be seeing in the waveform here. So the waveform for the counter, there are two waveforms here. The first one is based upon ABC condition. If A bar BC bar is encountered, what happens here? So you have counter next, counter reg here, and once again you see it's a multi-bit precision, and it is in decimal here. So it has been put as decimal. We'll see that in the model sim later on. And so you see that we had to increment the counter only if condition is satisfied. The condition is A bar BC bar, isn't it? So that happens here. So you can just go through this. These three are the waveforms here. You can see when it happens. So it's happening here. So this is 0 here. Is that the one? Yes. Right. So this is 1, 1, 0. Is that the condition that we had set? Okay. The same condition? No. So we'll come to that later. We'll verify that from the thing. We'll just see the counter output. So it's clearly counting here, and it's counting because advance count is going high. So what we need to verify is whether it is going at the right time, and this is happening at some point of time. Let us see why it is happening here. We'll come back to that. And as mentioned before, we had an assign statement for counter register increment outside the thing. So this will go in advance when compared to this. That's what you are seeing here. See, after when it is 0 counter, next is already 1. So in advance it computes. So you save time, thereby you speed up the operation. Frequency of operation is enhanced because of that. So it starts counting 0, 1, 2, 3 all in decimal here, and so is the case. This is quite a long one. So I had taken the very first few of this, and then at the fag end another file. So you see here, because advance count is 1, counting is taking place, and this got reset here because of the reset pulse here, right at the point here, and this is the clock waveform. This is ABC here. So now let us see at what point of time reset count is going high. This ABC is here. This is ABC. So what you have here is 1, 1, 1, right? Let us see that. Okay. So this is reckoned at positive edge of the clock. So it sees 1, 1, 1, but that is basically an assigned statement there. And so for 1, 1, 1, let us see the power pointing. So advance count for 1, 1, 1. ABC each will have to be 1, right? This is a combinational circuit here, and so what you have here is that's why it is going high here. That reset count, this one, right? I'm sorry, advance count. Reset happens only when it the count touches 255. So are you convinced about this? Same. And we have reset count happening. Now you see this advance count is 1. It has been 1 all through. Had you gone through the model sim waveforms completely, you will be convinced it was high. So I am putting only the end point, how it leads to the final goal. So you see here, count next is again always one count ahead of count register. This is the actual output that we desire. And when you see here, it happens that 255 is here. This is for the counter edge. That's what we when it touches 255, right? This being a combination circuit, it goes high. You see, for so long as it is 255, it goes high. So this is nothing but the reset counter. So when it touches 255, the counter is reset. That's what we want. If you desire other than 255, you can put any other value straight away in decimal. That's the advantage of it. After that, again it folds back and resumes the counting, because it is an eternal counter as such. So that's how the functionality is. Once again, the time base you can see. In fact, it has taken plenty of time because it has gone through 0, 1, 2, 3, etc. up to 255. It has counted 256 rather totally. So many clock pulses it has gone through. So you can find out how much it is here, around this, right? But we started not on 0, but after time lag. So you can find out, I think 20 nanosecond we did, 20 into 2 to 6. So plus some extra time because reset was applied and so on. You can always go and verify this. So this completes the counter as such. There are more circuits on sequential, and we'll see that in the little more details on this model sim in the next class. Thank you.